All right, so in this video, we're going to talk about different flow models. So how fluid moves through different types of reactors, different types of pipes, and kind of what are the models that we use in order to design reactors moving forward. So environmental engineering process design, when we're designing things, especially for water and wastewater, your flow rate and your detention or retention times are absolutely critical design parameters. So flow rate, retention time, or detention time. Those things are going to determine the size of your reactors, and that's a really, really critical component. If you think about a large system like the system in Omaha, you can have a big sized reactor. But if you think about a very small rural community in Nebraska, you can't have those big style reactors. And so things like flow rate and retention time drive the size of things in your system. So they are absolutely critical parameters. So flow models are going to tell us how the fluid moves, and it's going to help us to determine which design scenario is the best in a given scenario. So when we talk about continuous flow systems, they can either be what we call ideal plug flow, sometimes this is called piston flow, or we can have ideal completely mixed flow. So these are the ideal conditions that we could potentially have for flow. So let's talk really quickly about those ideal scenarios. So an ideal plug flow regime is basically whatever particles are entering at the same time, leave at the same time, and they leave with the same velocity as the other particles around them. So there's no longitudinal mixing, so that means you basically just have a plug of material that moves through and it doesn't mix up and down, and it doesn't mix side to side. And generally we see plug flow in systems that have a large length to width ratio. So you can think of plug flow as in pipes, distribution pipes or sewers. That's kind of a good example of plug flow. And what you'll see at the bottom is kind of a visual representation of this. So basically your plug of fluid that you're considering at any time is in kind of that yellow-orange color. And as it moves along, all those particles in that plug stay together and they stay at the same velocity as they move through the system. So that is ideal plug flow. The other ideal flow regime that we have is ideal completely mixed flow. And basically fluid elements are immediately uniformly dispersed in the system. It's a completely mixed, uniform mixture. Vessels could be circles, squares, rectangles, but basically they're not that long tube that we see with a plug flow reactor. So what you'll see at the bottom is you'll see this little faucet that's dribbling water in. And over time, as you move towards the right, you're going to see that almost immediately that's going to be uniformly distributed throughout the vessel. And then over time, the concentration of whatever that is going to disperse because it's most likely going to leave the vessel as well. So this is ideal completely mixed flow. So the two cases we just talked about are ideal scenarios. So these are the limiting cases, right? This is either plug flow or ideal completely mixed. In the real world, we're somewhere in between, as is kind of normal with these types of systems. So somewhere in between is what we call plug flow with dispersion. So that's what we're going to term it in this class. If you end up doing FE review, other classes at the university, whatever it happens to be, this is sometimes called by different names. So I've put a couple of the different names down here at the bottom. Sometimes it can be called dispersed plug flow with longitudinal mixing, arbitrary flow, intermediate mixed flow. They all mean the same thing. We're somewhere between ideal plug flow and ideal completely mixed solutions. So let's talk really quick about three different flow cases that we can have. So what this diagram is showing us is it's showing us plug flow in the real world, so not the ideal scenario. And you'll see that we have a long length to width ratio. This is a pipe. So the flow is moving from left to right in the system. So if we look at the pipe, initially we have white dye, right? It's just white inside that pipe. And then at some time, we decide to add some red dye right before we enter the system. Let me grab my laser pointer so you can see. So we add some red dye to the system. And that red dye is going to act as a tracer. So it's going to give you a sense of how that red plug of fluid is going to move through the system. So once that dye has been added to the system at the front, there's going to be this little plug of red fluid that's going to move. In plug flow, that little plug of red fluid is going to move all as one unit, same as the ideal case. And then over some time, it's also going to reach the end of the system. So you add some dye and it moves along together in this one line in order to move through the reactor, which in this case is a pipe. In this next scenario, this is the completely mixed flow. So same idea, we're going to do kind of what we call a tracer study in order to kind of understand this. I'm a very visual person, so I like to use colors to hopefully help you understand just a little bit. So you'll see same kind of scenario, except now we don't have a pipe, we have a circle, and there's white dye inside that circle. Flow is still moving from left to right. At some time, we decide to add some red dye to the system, and you'll see that what happens is down in this third panel down here, all of that dye doesn't move like a plug through that circle. It immediately disperses and it's uniform throughout the system. Now that amount of red dye is very small, so over time as it gets dispersed and flow keeps going through the system, we're going to end up with kind of this pink scenario coming, right? We're going to have dye dilution basically. So that red plug, it gets dispersed within the white, and the white is just still kind of moving through it as normal. So that over time we eventually get back to the original condition. So that's completely mixed flow. When we talk about completely mixed flow, I want to just show the equations for the mass balance for this one as an example of how you can kind of use some of the mass balance principles that we're learning in class to do this. So if we want to say what the mass balance looks like in words, we basically say that the proportion of concentrations is related to the exponential relations between time and retention time. So what does that mean? So basically, if we think about that completely mixed flow scenario, after time equals 0, right? The input of dye equals 0, right? So the dye gets put in the system at time equals 0. So there's no more input after time equals 0, right? There's no reactions occurring in the system. So if we think about our mass balances, that means our input term is 0, our generation term is 0. We have some kind of an output, and we could potentially have some kind of an accumulation in the system. So that means that our mass balance comes down to this form down here. The change in concentration times the volume is going to be equal to a decrease in the concentration times flow rate times the change in time. And so like we've been doing in class and as we've been talking about with mass balances, you can integrate, take all the variables to the same side of the equation, integrate, and we get down to this form down here. And this form of the equation down here at the bottom is basically what that sentence says above. So the proportion of concentrations, right? The fraction of concentration at time 1 versus concentration at time 0 is equal to the exponential relations. So there's an E here between time and retention time. So you'll see there's two forms of the equation here. Recall that if you have a flow rate, a Q, over a V, which is a volume, flow rate over volume is equal to what we call retention time. So 1 over retention time in this case. If you have a volume over a Q, that's a retention time. And that's, again, remember, represented by a theta. So that's how this particular mass balance works out for a completely mixed flow reactor. This flow regime is the one that we're going to see most often. So it kind of looks like plug flow, right? But there's some dispersion happening. So we add some dye to the system, and what you'll see here in this second area is that there's now longitudinal mixing. So basically what that means is the fluid is expanding from side to side, and there's some mixing going on, almost like it wants to disperse within the pipe, but it can't disperse within the pipe completely because it's still moving forward through the pipe. So you can see it kind of moves forward like a plug flow reactor, but there's some dispersion, especially in this middle case, where it's not 100% a perfect cylindrical plug anymore, moving through the system. So again, this type of flow is going to be the flow that we see most often when it comes to actual environmental engineering process design. So let's do a quick summary of everything that we've learned in this particular video. So what are some key concepts related to flow models? First, plug flow with dispersion is the most common type of flow we see in environmental engineering, unit process, and operation design. If we know how things are flowing, we can better design reactors and conveyance systems. So basically, if we know how things are moving, how fluids move in our system, we can get a better sense of how to design things. What types of reactors? Is it a cylindrical reactor? Is it a pipe? Is it more plug flow? Is it more completely mixed? Those tell us something about sizing and volumes in these systems. And not only reactors, but we can also size our conveyance system. So things like distribution systems, so getting water from the water treatment plant to a location. And then our sewers, getting the effluent from a location to our wastewater treatment plant. So that's why this is important. Finally, to kind of keep this in the vein of what are the key parameters that you need to know if you're designing systems, same as we've been talking about with kinetics and with mass balances in class, the initial and final concentrations are going to be important here because we're still doing mass balances, we're still looking at kinetics. The time it takes to flow or move through a pipe or reactor is really important. The volume and the size of the reactor is important, and the flow rates are important. So all of these variables work together in flow models to give us a sense of how do we actually design these things in practice so that they're sized properly and they're getting the removal efficiencies that we're looking for. So that's going to wrap us up for flow models. We'll discuss this a little bit more in class, specifically looking at how do you apply these to actual real-world case studies.